Good morning. We continue our lecture on diffusion in solids, and last class we have learned that diffusion is a process of mixing, and we are going to consider particularly this process of mixing in solid state. Now, as we have seen last class that and it has been discussed in detail that this movement of atoms, they are perceptible in case of liquid and gases, and we can feel or we can see even in certain cases how the process of mixing continues through a phenomena of diffusion in liquid and gas. But the method of diffusion in solid is also exactly same. The atoms in crystals, they are not stationary, they keep moving, and as a result there will be movement of atoms in a particular direction in solids, and this is what we considered last class, and we have talked about the phenomenology of diffusions, the phenomena. We also looked at the laws of diffusion, laws that govern diffusion. We also looked at few problems of diffusion couple, how a concentration, if there is a concentration gradient, how does this concentration change with time. We also looked at the effect of temperature. Today, we shall look at a little more detail about the mechanism of diffusion and what happens if you have different species, whether the both species they move at the same rate or different, and if they are different, what effect does it have on the concentration distribution in the solid. Now, while looking at some of the solutions in the last class, I think what it came out that the process of diffusion can be simulated as one of random walk, and it was, and this expression was partly derived up to this, but this also can be you can simplify it, you can add these terms and then you get a factor like this, and here each of these, when you, this is actually a dot product. So, each of these cases there are dot products. So, here also this is a dot product, and what we have done here is basically if you have one vector, say random walk in this direction, another random walk in this direction. So, this is R I, this is R, let us say I plus j. So, in that case there is an angle subtended and we call this angle I plus j. So, this dot product R I dot R I plus j, this will be equal to magnitudes of R I, magnitude of R I plus j times cos theta, that is I plus j, the specific angle. Now, we can always say that average distance or step size of the movement, if it is equal to lambda, then we can say this will be equal to lambda square cos theta. So, this is what has been done over here. So, clearly what you see on the slide is this, if you take this common, because this sum will be n times lambda square. So, basically this you can take common. So, you have a factor which is a function of the direction, and this directionality is quite important. If this is totally random, if these materials these atoms, they are free to move in all directions, which is quite possible in certain cases, they can free to move, then this sum total of this sum total of cos theta will come out to be 0, because in certain angle this will be positive, in certain direction that cos theta will be negative, and therefore, the total sum may come out to be 0. But in cases where there is a directionality in the movement, in that case this is cos theta, this may not be equal to 0. So, there you can have a orientation factor which is or directionality factor, and which is shown here. So, that means that average distance of a random walk, will be equal to lambda root n, and there will be a concentration factor. Now, let us look at the mechanism of diffusion in crystalline solids. Solids mostly that we will be dealing with, they are mostly cubic, majority of the metal, maybe 2/3 of the all metals which are known, they all have cubic structure. Cubic structure has very high symmetry, and therefore, for all practical purposes we can assume that diffusivity is same in virtually all direction in most metals, which may not be true in certain metals where they have hexagonal and other with a low symmetry. It may be different in different direction, but let us not go into that detail, and we will look at diffusion mostly in cubic solids. And this diagram pictorially represents a systematic array of atoms, and here the material often has some vacancies, say like some of the places the sites are vacant. So, these are the normal sites, this is a 2D and these are the normal site. Now, how can atom move from one place to another? So, one mechanism is, if there is an atom in the interstitial gap, this is a normal lattice site, this is a normal lattice site, and in between there is an interstitial gap. If there is an atom here, and if it tries, if it can move over here, possibly when it moves, gap here is smaller, it may have to push it a little and then come here. So, this is one mechanism of thermally activated motion of atoms in solids or diffusion. So, basically this is called interstitial mechanism. Another thing which we can think about, the atom can exchange position with vacant sites. So, if there is a lattice vacancy at this lattice site, there is no atom here. So, an atom which is located here can move to this vacancy. So, this is called vacancy driven motion of atom. We can also think about certain things like site exchange. So, this atom, these two which are the nearest neighbor, sometimes this goes here, this goes there. There is also a mechanism called indirect interstitial movement. So, basically if what happens, there is an atom here, say somehow this often can happen in radiation damage, an atom is pushed into interstitial site. So, this can push this atom to interstitial and can occupy this lattice site. This is also through movement takes place through interstices. So, this we call it indirect interstitial mechanism. There is also a mechanism called ring mechanism, that means atoms they can exchange like this, an extent of this site exchange, and here this movement is like this. But out of this we will see that there have been lot of experiments done, and possibly it looks that vacancy and interstitial movements are possibly the mechanisms which can explain many of the phenomena of diffusion. Now, let us look at diffusion of carbon atom in alpha iron. Now, we know that alpha iron has a BCC structure. So, BCC structure which is shown over here, and the carbon atoms are present in the interstitials, and the likely that interstitials which are shown here in the figure with color red. So, this one, these are the interstitial sites, they are called the octahedral sites. Now, look at this plane. This plane has normal atoms, iron atoms located at the corner, and we have carbon atoms located. These are likely sites, it is not that all of these sites will be occupied. And let us consider the next similar plane is this, and here also there is an atom over here, and these are the interstitial sites. Now, if you look at this atomistic mechanism, say if there is a carbon atom here, if it has to move to this plane, the nearest site here, but this is occupied. So, this atom is not able to move, but look at this atom over here, which is an interstitial atom over here, and this can move to this point. So, that means not all the interstitial atom on this plane have the ability to diffuse or move to the next plane. So, that means we have to calculate from the atomistic mechanism, if you have to calculate or estimate that magnitude of the diffusivity, in that case or jump frequency, we have to look at how many atoms or how many interstitial atoms are likely to move, or what is the probability that